Hello students, I'm Argen Kukitaev and this is a video on state space models. I call it motivation, but basically it's going to serve as an introduction to the subject. So the subject itself is quite involved. It can be, it usually is an advanced econometric statistics curriculum, right? So they don't teach it in the introductory level, so chances are you're studying for master's or PhD, and that's why you might be taking something like state space modeling course. So in this brief video, we are going to learn about the basics of state space models, and we will actually implement a linear Kalman filter, a centerpiece of this approach. Then we will apply it to model a process for United States inflation time series. Although it's a brief video, we will cover quite a lot. And although we don't do derivations in this video, I hope that after completing this little lesson, you will be able to read more advanced text with rigorous treatment of the subject and so on. So at least it will be easier for you to navigate those texts. And the books on time series are quite thick sometimes on state space models. So this is like a classic book on by Andrew Harvey, one of the like titans of state space modeling and time series, theoretical time series analysis, about more than 500 pages, just pretty much state space modeling alone. But we are will be following this text, which I give you the links. It's time series analysis and its applications by Shumway and Stauffer. There is a chapter dedicated to state space models. Again, it's a subject in itself, and it's impossible to cover the whole thing, but we will cover surprisingly a lot. You will see. Okay, so why don't we move on? So we'll start with a setup of a state space modeling, and setup is actually interesting. It's based on the idea, I suppose, that we're observing some maybe time series which are driven by something which is not observable, by some other hidden state which we cannot observe but we want to know about. Right, so it may sound familiar to people who are into like conspiracy theories, which are very popular lately. It seems around the world, especially they became popular during COVID, right? So things are not as it seems. Like there's always some underlying forces and so on, and people are trying to figure out what's going on and so on. So I'm joking, obviously, here, but this idea that we want to learn about some drivers, some factors which are not observable through what is observable. This idea is quite common, and you may have seen it in different manifestations in different areas of finance and economics. So, for instance, principal component analysis, right? So you're observing some series, but you're saying they're driven by hidden factors. Latent factor analysis or factor analysis in econometrics and so on, and the list goes on. There's quite a few ways of doing it. So basically what state space model does, it creates, or rather it states, these set of equations, and some of them, or at least one of the equations, is called state equation. So the state equation describes how that hidden state evolves over time. And that's what we really want to learn about. And then there's another equation which is called measurement or observation equation. So basically we have two equations and they form the state space model system of equations. And as I said, as I promised, the discussion in this video is going to follow the Shumway and Stauffer fourth edition of their book called Time Series Analysis and its applications with R examples, right? So let me click on here, so we will bring it up. This is how the book looks right? So this is the book we're going to follow. You don't need that book to actually understand this video. But if or rather I would even say you can use another book which has, or any other book which describes state space model. So my hope is that my today's lesson is going to help you basically read this type of books. Okay. Right. Again, as I said, chapter 6 is dedicated to state space models in this textbook. Okay, so we have state equation and measurement equation, and basically fitting the model, these two equations, their parameters, to the data set, which is basically what we measure, right? Measurement observation equation. So we fit this model to what we observe, and we are able to, or at least we hope we're able to see the evolution of state equations. So in that regard, this set of equations and state space model in general sort of transports you from what is observable to some other space. Like we're in the space of observable. We see all these variables and they form our space. And then we transport ourselves through fitting the model into the state space, in a different space. So that's why it's called state space modeling. We transform from what is observable and measurable into something which we're trying to measure, right, which is not directly observable. So let us look at the state equation first. So the state equation is a vector autoregressive process, and if you are taking my time series course, then you should have some idea of what is it, because we covered it, right? So it basically, think of this process. If you're not familiar with vector autoregressive, then at least you know what is autoregressive, so this should look familiar somewhat, right? So you have this state, which is a vector in this case. It's not just one observation, but multiple. So it's easy, like if you're in finance, it's easy to think of a vector as, let's say, interest rates. At any given point of time, you have multiple interest rates, right? Short, long, 1 month, 3 months, whatever, 10-year, and so on. So you're observing all these interest rates at once. You can add more variables, GDP, unemployment, and so on. All of these variables form a vector, which we capture every period of time. So now this equation describes how this vector evolves. So if previously the vector was x, then today it's in the next period it's going to become xt. So it was xt minus 1 period, and now it becomes xt. How? Well, you see the old state is multiplied by the matrix in this case. So if it was univariate case, this phi would have been just an autoregressive coefficient. But because these are vectors, this phi is entire variable, right? So you entire matrix. So you multiply this matrix by the vector of the state, and you get a new vector of the state. But not only that, we in this equation we also add two more terms. There's first of all the familiar error term, but in this case error is a vector itself, because for each of these elements of the vector you need its own error. So basically the error is an error vector. So if you have p variables, p small cap, right, p dimensional vector, then we have p errors here. Now this y variable is an exogenous variable. So xt is an endogenous variable of the state, which is hidden, which is not observed directly. It is influenced by some observable exogenous variable. So imagine if you're trying to build some kind of an interest rate model, what can impact it? Maybe stock market, maybe GDP, who knows, unemployment, and so on. So these other vectors, which are not modeled, which you are not trying to forecast, which are known, are captured in this UT. So this should be similar to, in ARIMA framework, it should be similar to something called ARIMAX, ARIMA with exogenous variables, right? So we have this vector. Again, it's a vector autoregression process for the state, which is not observable. Great, and this phi and this epsilon are matrices again, right? So they're multidimensional matrices. So in this case, if X is p-dimensional, then phi matrix is P by P, right? The autoregressive matrix. And now the epsilon matrix, which incorporates the impact of exogenous variables, is going to be what? It's going to be P by R if the exogenous variables are r-dimensional. So think of like r number of variables which are impacting our endogenous variable xt, then this epsilon is going to be P by R matrix. Okay, and then the errors are, in this case, in the simplest case, are normal. Standard normal, not standard, but normal errors with the mean 0 and the Q. The Q is being the variance matrix, variance covariance matrix of the errors. So the Q is also P by P matrix. Okay. Okay. Now, as I said, we do not observe directly the state, but we can measure it, and that measurement is in this variable y. So we can observe the variable y, which is driven by the state x. All right. So in the simplest form, we could say, well, our y is some kind of transformation of x, and then the same exogenous variables are there, but a different matrix gamma, and plus its own error. So this is, you can think of it as a noisy measurement of x, right? So this is x, which we do not observe, but we observe y. And there is some hidden state x, and we actually want to learn about this hidden state, and we want to learn about, most importantly, these matrices phi, epsilon, a, and gamma. These are all unknowns. These are all parameters of the model, potentially unknown. You may know some of them. Now, the errors here, measurement errors or observation errors, are also stochastic and from normal distribution, but their matrices are. So now notice that the dimensionality of what we measure and what the hidden states can be different. So for instance, if yt is, we're saying q-dimensional vector of measurements, then the matrix, this R matrix, which is variance covariance matrix of measurement errors, is going to be q by q. Now, what is this A? So A, one way to think about it is, imagine that your X is measured, let's say, in inches, and Y is measured in centimeters. Then A would have been simply the conversion. Or maybe X is exchange, like let's say yens, Japanese yens, and Y is dollars. Right? So then A could be exchange rate, and so on. So it's some kind of a scaling or conversion of the measured state into, hidden state into a measurable metric. Okay, again, so in our setup, think of this. We can collect the data on Y. So maybe these are indices, economic indicators, and so on. We observe them. But then X are some other variables which are naturally describing the internal state of the economy, and we want to learn about those. So we, once we look at this little example, it'll be a little bit clearer, right? So we'll look at this small example, which is not really in economics. It's from global temperature, and this example is in the Shamway and Stoffer's text, example 6.2. So they have a chart there, and I'm going to bring it. So here's a chart. I mean, it may not be very clear on the video. Right, so I'll explode it. So you will see there are two variables here shown on the chart. The red one is a temperature, some sort of an index of the global temperature, which includes both land and ocean temperature series, while the blue line includes only the land. So the difference between blue and red, generally, apart from them being measured differently, that one of them includes ocean and the other one doesn't. But conceptually, they are supposed to measure the same thing, some sort of global temperature, right? So, and that's why it can be appropriate to try to model them as a state space model. So what we're having here, so we say, well, there's some temperature temperature of Earth, right? And maybe we'll say X. We do not observe it directly, but we're observing Y's, some kind of a global temperature index, which includes oceans, and the other which it doesn't. Maybe they have different collection methodologies, data processing, and so on. And even the concept of the Earth temperature is actually tricky, right? Because Earth is a pretty big body. It's like 6,000 kilometers in radius. So when we say the temperature, I mean, how do you get average temperature? There's no easy way of just saying, okay, what's the average temperature? So you have to collect temperature from different points on Earth, from different weather stations, and the density of stations is very different in different parts of the world, and maybe measurement errors are different and so on. But anyhow, even coming up with that one temperature, one number is a tricky proposition. Right, so anyhow, somehow they came up with two different data series, one with ocean temperature, one without, Y1 and Y2. And the idea here is that they reflect this one-dimensional or univariate temperature. There is some number we're saying, and using these two series, we want to find out what is that number. So our measurement equation becomes simply, we have this one number, and then look at coefficients 1 and 1. This A coefficient conversion is going to be 1 and 1. So it's temperature directly. So there's no, it's like identity basically. But there are some measurement errors, nu1 and nu2. Now the temperature itself, the state of it is, we're going to posit that it is a random walk process with a drift. So you see my new temperature is my yesterday's temperature plus some drift and some shock, temperature shock from whatever it is. And now we can try to estimate this model using state space model. Okay, so in this case we can see how these parameters phi, epsilon, a, and gamma are set up for this kind of a model where our y has two dimensions, a two-dimensional measurement. So our basically here when we are talking about the measurement, we said q is a dimensionality. Well, q is equal to here, right? But by p is equal 1. P is a dimensionality of a state. So we're saying p is equal 1, q is equal 2. Now this phi is simply ones. It's a matrix of ones. And then our epsilon is going to be delta, right? You see, epsilon is a coefficient on exogenous variables. So we're using an intercept, a very simple exogenous variables, which is always equal to 1, similar to regression, right? So that's why our epsilon is delta. But gamma is 0, so we don't have gamma. And that means that in our measurement equations, we do not have exogenous variables. Okay, so that's why gamma is 0, and again, as I said, their exogenous variables are dummy 1, and I think we're done, right? So yeah, and that's all. Phi was here equal to 1, and phi 1 means, by the way, unit root. So this is a very simple example of setting up state space model for a process, which is quite reasonable, right, to imagine. So by the way, you see people who created this model there, it's from the textbook, obviously. They are assuming there's some kind of a drift in global temperature. So that's why they call it global warming example, because they assume there's some kind of a warming, there's some kind of a trend. And once you estimate, you can look at this delta, whether it's significant or not, and then decide for yourself whether the globe is warming or not, or maybe it's just a random walk with like a lot of noise. Okay. So that was a very simple model in a state space, very simple state space model, right, for a simple project like that. So what we will learn later is that actually, despite its seeming simplicity, so you see, you look at these two equations, oh, it looks very simple. Despite its seeming simplicity, this is a very flexible framework, and flexibility comes from the fact that x is a vector and y is a vector, and you can do very cool things because they are vectors. So this state space model allows for representations of all kinds of different models. such as ARIMA, very well-known ARIMA. But we will see a few things. We will ask ourselves like why actually we want to implement other models as SSM, and we will learn that, as I said, the main thing is flexibility. We can do it, but then we will learn something called Kalman filter. It's a very fast and reliable way to estimate and forecast these models. And the second thing, we will see that state space models allow for very convenient handling of missing values. That's a big issue in economics. We always have some missing values here and there. So we will see that by converting our favorite time series models such as ARIMA into state space model, we not only are reusing some code which was written for state space models, but we are also using the advantages of this fast Kalman filter and missing value handling. Now let's get into our main example of this video, right? We are going to talk about PCE inflation series modeled at state space models.